Imagine waking up tomorrow and nothing works. Your phone turns on, but it doesn't connect. The bank opens, but your balance doesn't load. The hospital cannot access medical exams. Satellites lose signal. The internet begins to fail country by country. There is no explosion. There is no war, only digital silence. And all of this happens because something microscopic ceased to exist. Something smaller than dust, something invisible, something that begins with sand. But it's not just any sand. Today you will understand how a handful of grains became the brain of modern civilization, and why, if this chain breaks, the world wouldn't last 48 hours. Here at Factory Manufacturing, we unveil the secrets behind the fabrication of products you use every day. From microscopic components to gigantic machines, we show how engineering and technology unite to create the incredible things that move our world. If you're passionate about industrial processes, manufacturing, and technological innovation, you're in the right place. Subscribe to the channel and hit the bell icon so you don't miss any video from our journey through the fascinating world of industrial manufacturing. Beach sand looks ordinary, but it is useless for manufacturing chips. It contains iron, it contains calcium, it contains invisible metals, and in the world of microelectronics, invisible means fatal. A single misplaced atom can compromise billions of transistors. The industry uses ultra-pure quartz. But not all quartz is suitable. Deposits must have extremely high silicon dioxide concentration and extremely low contamination levels. This drastically reduces the number of places on Earth capable of supplying suitable raw material. But what happens after mining is even more extreme. And this is where the fragility begins. Because when only a few places control the raw material, the entire world depends on them. After extraction, the quartz goes into giant furnaces. Temperature, nearly 2,000 degrees Celsius, hotter than volcanic lava. Inside these furnaces, oxygen is removed from the chemical structure. What remains is liquid silicon, bright, incandescent, almost alien. But that is still not enough. This is only metallurgical-grade silicon. To become a chip, it needs to become almost perfect, and almost perfect in the semiconductor industry is not enough. It must be absolute. It must be refined thousands of times more than the steel of a skyscraper. We are talking about a level of purity that challenges industrial chemistry itself. To become a chip, silicon needs to reach 99.99999% purity. It is transformed into gas, distilled, recondensed, recrystallized. Each cycle removes invisible traces. A single microscopic defect can cause million-dollar losses. Because when billions of transistors are printed onto a surface smaller than a coin, there is no margin for error. This is where engineering reaches the limits of physics. The purified silicon is melted again. A small crystal touches the incandescent liquid and begins to slowly rise while rotating. This process is called the Czochralski method, and it creates a monocrystalline ingot. This cylinder can exceed 1 meter in length, and every millimeter of it must have perfect atomic alignment. If there is vibration, imperfection. If the rotation is wrong, structural failure. We are talking about atomic level control, literally organizing atoms in perfect order. The ingot is sliced with microscopic diamond-coated blades. Each slice has thickness controlled in micrometers. These discs are called wafers, surfaces where billions of circuits will be built. After cutting, the wafers are polished until they become mirror-like. An irregular surface, invisible to the naked eye, can destroy months of production. Deviations smaller than 1 micrometer are unacceptable, because any imperfection becomes an electrical failure. There is no improvisation here. There is absolute precision. Now, the wafers enter clean rooms. The air is filtered thousands of times per hour. A single dust particle can destroy an entire chip. Some of these rooms are cleaner than surgical centers, more controlled than military laboratories. Workers wear sealed suits. But almost everything is done by robots. Airflow is controlled. The pressure is positive. Even the lighting is designed to avoid generating turbulence, because this is where the most complex process ever created by humanity begins: extreme lithography. Giant machines use extreme ultraviolet light. Each of these machines can cost more than an entire luxury building, and they are considered some of the most complex machines ever built, and there are only a few of them on the planet. This light draws circuits smaller than viruses, layer by layer, dozens of times. Alignments must be perfect. If one layer is off by just a few nanometers, the chip fails. At the end of the process, the transistors emerge, microscopic switches, on, off, 1 or 0, but billions of them together create something extraordinary. They process images, they perform calculations, they train artificial intelligence. A single modern chip can contain tens of billions of transistors, all operating billions of times per second. All of this in a piece of silicon smaller than a coin. It is absurd computational density, and if this chain fails, all of it stops. Not slowly, not partially. It stops all at once. The internet depends on chips. Hospitals depend on chips. Banks depend on chips. Satellites depend on chips. Modern cars depend on chips. Without silicon, the economy stalls. The modern world was not designed to return to analog systems. There is no manual button to restart digital civilization. Without microprocessors, supply chains stop. The planet's infrastructure is digital, and the modern world was not designed to function manually. If this chain breaks, there will be no explosion. There will be silence. Now imagine that, for some reason, global chip production stops. Not for hours, but for days or weeks. In the first 6 hours, stock markets panic. Payment systems begin to fail. Companies suspend operations for safety. In 12 hours, supply chains freeze. Ports cannot release cargo. Aircraft wait for digital authorization that never arrives. In 24 hours, hospitals switch to manual mode. Factories stop. Gas stations lose their systems. And then comes the question no one wants to ask: who really controls the technological heart of the planet? Because semiconductor production is concentrated in only a few places in the world, very few factories. If one gear fails, it's not just one company that stops, it's the system. And this is where sand stops being just sand. It becomes power. It becomes strategy. It becomes geopolitics. The modern world is not sustained by oil. It is sustained by silicon. And digital civilization has no plan B. Sand transformed into intelligence. Sand transformed into power. Sand transformed into civilization. From the desert to the data center. From the mine to the satellite. Everything begins with a handful of grains.